So it's my pleasure now to introduce to you Steve Furber. Steve is ICL Professor of Computer Engineering in the School of Computer Science at the University of Manchester in the UK. He completed a BA in mathematics and a PhD in aerodynamics at the University of Cambridge, and then spent the 1980s at Acorn Computers, where he was a principal designer of the BBC microcomputer and the ARM 32-bit RISC microprocessor. Variants of the ARM microprocessor now power much of the world's mobile and embedded computing. At Manchester, he leads research into asynchronous and low-power systems, and more recently, neural systems engineering. He'll talk with us today about neuromorphic computing, or brain-like computing. At Manchester, the spiking neural network architecture platform, which is nicknamed Spinnaker, is a computer for brain modeling applications that includes 1 million ARM processors and an interconnect fabric designed to support the very high connectivity of biological neural nets. I was very excited to learn that Spinnaker was just turned on this month, and so this should be a very interesting talk for us. Welcome, Steve.
Thank you very much for that introduction. The turn on last month was of the full 1 million core machine. We've been running a service on 500,000 cores for 2.5 years before that, so it was really just the final milestone. So I'm going to talk about a project which has been 20 years in conception and more than 10 in construction to build a machine that's both inspired by what we understand about how the brain works as an information processing system, and it's also built to improve that knowledge of the brain, because the brain as an information processor remains one of the great frontiers of science. We still really don't understand what's going on inside each of our heads. And so the Spinnaker project is intended to contribute to progress in that knowledge. Now, of course, we aren't the first people to be interested in understanding the brain. And 200 years ago in the UK, this lady was working with Charles Babbage, who had his early ideas for mechanical calculating machines. And Ada worked with him, and she thought about how these machines might be used to implement algorithms. To many people, she's viewed as the world's first computer programmer because of the way she thought about using this machine. So I like to think that there was a time when all computer programmers were female, and unfortunately the pendulum's swung too far the other way since then. But as well as thinking about programming, Ada wrote copious notes, and most of these notes survive in a library in Oxford. And among those notes are the thoughts that I've put on this slide, where she talks about having hopes of getting cerebral phenomena such that I can put them into mathematical equations. I hope to bequeath to the generations a calculus of the nervous system. Now, that was high ambition 200 years ago. Indeed, I think if I wrote words like that on a research proposal today, it would be rejected for being hopelessly overambitious, because we are not close to achieving Ada's original ambition of understanding, in some theoretical sense, what's going on inside our heads. If we come a bit closer to today, I live about 10 miles south of Manchester in the UK, and quite close to me is a fairly ordinary house which has a plaque over the gate at the side, and this plaque says that this is the house where Alan Turing lived his last few years. Turing came to Manchester because Freddie Williams and Tom Kilburn had built the first machine that implemented Turing's big idea from the 1930s of the universal computing machine. And Turing came to Manchester to use that machine. Now, while he was in Manchester, he worked on a number of topics, and we saw one example in the previous talk of looking at morphogenesis, how nature breaks symmetry as cells divide. But he also wrote his seminal paper with the title on computing machinery and intelligence. And in that paper, he begins with the words, "I propose to consider the question, can machines think?" And he, of course, decides that's not a very good research question, so he turns it around into what he called the imitation game, the test for human-like artificial intelligence. He called it the imitation game. We all simply know it as the Turing test for human-like artificial intelligence. And in that paper, Turing reckoned that all the machine would need, compared with the Manchester Baby, was more memory. The Manchester Baby machine had 128 bytes of memory, and Turing reckoned that a gigabyte would be about right, and that machines might have a gigabyte of memory by the end of the 20th century. That was a remarkable prediction when you think he was starting with a machine with just 128 bytes, that 50 years later you might have 1,000 million bytes, but that's, of course, roughly when you did have machines on your desk with 1,000 million bytes, and hopefully the slides now come up, yes. But despite, at the turn of the century, machines having a gigabyte of main memory and being 1,000,000 times more powerful than the Baby, they still wouldn't pass Turing's test. And Turing would be very surprised that even today, no machine has convincingly passed his test for human-like artificial intelligence. In the opening talk this morning, we heard that although there's been much progress in niche machine learning applications, there's been very little progress in understanding what it takes to build a machine with human-like intelligence. And my take on why human-like intelligence has proved much harder than Turing and many others since him have thought is because we don't really understand natural intelligence. And natural intelligence, of course, is based on how the brain works, and we don't understand that. So I think the prospects for developing human-like artificial intelligence will not be very strong until we know a lot more about how the brain works, and that's why my research has moved in that direction and is motivated by these two headline questions. Can we use the formidable computing that's now available to us to accelerate our understanding of brain function? And as we learn more about the brain, can we use that knowledge to build better computers, for some value of the word better? Now, we've been doing this for a long time, and of course over the last 10 years there's been this parallel development with quite different motivation in industrial machine learning systems. And here's an example. Again, we saw a picture very similar to this earlier. It's a deep network where at the left-hand side there's an image. I believe traditionally it's a cat. And then this flows through many layers of neural network until it gets to a classification stage at the right-hand end. And if that says it's a cat, everybody's happy. But if it says it's a dog, you then feed the errors back and you adjust hundreds of millions of parameters until the network starts to say it's a cat very consistently. Now, Google was rightly very proud when they trained their network on 10 million examples of cats, and it became very good, possibly even superhuman, at recognizing a cat. But my observation here is that if you take my 2-year-old grandson and you show him one cat, he will then recognize cats for the rest of his life. He doesn't need to be shown 10 million cats, one is enough. And so there's something very different going on between the industrial nets and the biological system. Now, it's not a fair comparison because, of course, the Google net starts with all its parameters effectively scrambled, whereas my 2-year-old grandson has had 2 years to build a fairly sophisticated model of the world into which cats fit very nicely. But there's still some kind of difference of principle at work here. These artificial nets use abstract neurons. They produce continuous outputs. They're predominantly feed-forward. although there's growing interest in a bit of state and feedback, and they're trained through this gradient descent algorithm. If we look at a similar picture of a very simplified view of the brain, the outer layer of the brain is the cortex, then the picture looks much more complex. And biological neurons communicate predominantly by spiking. So every so often they go ping, and all your thoughts as you sit there listening to me or wondering what you're going to have for lunch, all those thoughts are patterns of pings flowing between the neurons inside your head. You can see that the flow isn't simply left to right or unidirectional. There's very complex feedback mechanisms set up in here. And unlike the artificial nets, biological nets are always sparsely connected. So in biology, if population A projects to population B, each neuron in A connects to no more than about 10% of what it finds available in B. And that's quite different from today's industrial nets. The other big difference, of course, is we don't know how this biological system is working. We still do not understand how these complex nets achieve useful function. If you want to compute these networks, then the machine of choice for an industrial network is the GPU. Because these industrial networks use dense matrices, and GPUs are very good at processing dense matrices, then they're very effective in performing the required computations. This particular NVIDIA box is about 3 kilowatts, and we're learning to use lower precision, but that's the engine of choice. If you want to model biological nets, then in detail you need something like this IBM supercomputer. Now, this is a supercomputer conference, so you all think that's a good thing. And now you can deal with sparse connectivity, and you can communicate using spikes, but your power requirements have gone from kilowatts to megawatts. But of course, there is this other technology which is much closer to how the brain works. And again, this example is from IBM. This is the True North device, where there's been effectively a complete re-architecture of the processing system. The memory's been brought very close to the computation. And now you can implement these spiking networks in biological real time, which in general you can't do on conventional supercomputers. And the power requirements have gone from megawatts down to milliwatts. So we're looking at a huge range of energy efficiencies in modeling these sorts of systems. Now, neuromorphic technology, because it looks so similar to industrial networks, which have gained a huge degree of application over the last 10 years, it's attracted commercial interest. And you can see this in the form of both large industry, where I've mentioned IBM's contribution already. This year, Intel joined the fray with its Lovelace chip, which is a very aggressive piece of silicon for supporting spiking neural networks. There are startup companies in Zurich. Innovation has spun out of the long-established neuromorphic work at ETH in Zurich. Chronocam has spun out of the Paris Vision Institute. And in Manchester, there is a startup that's using our technology to try and develop commercial event-based machine learning systems. So there's industrial interest, but to date, there is no compelling demonstration that any of this neuromorphic technology offers commercial advantage. And if you look at the offerings of industry, for example, the Intel Lovelace chip, that's a research prototype. It's not a full product. Intel is very actively encouraging universities to take this up and see what it can do. But until that compelling demonstration emerges, the commercial side will progress relatively slowly. Now, what we've been doing in Manchester over this period is the Spinnaker project, as you heard in the introduction. And we set ourselves the challenge at the outset of seeing what we could do if we could put 1 million small processors into a machine to support real-time brain models. It was very clear at the outset that even with 1 million processors, you're a long way short of being able to model the full human brain, but potentially you can model something of the scale of a mouse brain. In principle, you can get to about 10 mice. In practice, we can probably do about 1 whole mouse brain on this machine. The machine has many similarities to the high-performance computers that are the main subject of this conference. It's a highly parallel system, a regular mesh of nodes. Each node in Spinnaker has a compute layer and a memory layer. The contrast with high-performance computing is that it's based on very small processors rather than high-end floating-point systems. So we can build a chip, and the first 5 years of the project went into the design of this chip. It's not particularly aggressive technology. We put 18 cores on the piece of silicon, and then we package the silicon with memory in a 2.5D packaging structure, and we can then basically tile a 2D surface with these packages. If we look at the chip itself, then again, this looks quite similar to a number of HPC chips, with the difference that the processors are very small here. They're very simple, low-end integer units, and the reason there is because they are the most efficient in terms of their compute. They're not the most powerful, but they're the most energy efficient. And on the right-hand side here, you can see there's a light blue area. The processor is in there somewhere. We're never quite sure where. The memories that the processor uses most often are immediately next to it, and this is in order to achieve efficient operation. My model of the energy required for a computation is it's the number of bits you have to move multiplied by the distance you move them, and so you minimize energy by minimizing distance. And here, the frequently used code data moves about 1 millimeter when it's used. The less frequently used data is accessed to the external memory chip through the orange port on the left, and that's about 10 millimeters away. All of that looks fairly conventional. It's just a sea of processing units, but made with small processors. The innovation in Spinnaker is the way we connect those processors together, and that's the red bit in the middle. In Spinnaker, when a processor that's modeling a neuron, and the model is just a piece of software, so it's very flexible, when that model wants to generate a spike, all the processor does is drop a packet saying that a particular neuron has spiked into the communication fabric, and the fabric has all the information about where that spike is going, and it's typically going to many places. So the fundamental communication protocol here is multicast, with the routes managed by the interconnect fabric. So a spike becomes a small packet. That packet then has to be delivered to hundreds or possibly thousands of different places across the machine, and that delivery has to be completed to all of those places in a small fraction of a millisecond in order to achieve the biological real-time target. If we look in a bit more detail at how the routing works to support this multicast system, it exploits the fact that biological neural networks, the graph that describes their topology is mostly modeled as static. At worst, it's modeled as very slowly changing. And so we can store the information that describes that graph in the routing fabric itself. A spike becomes a 40-bit packet, so these are very small packets. We're carrying very small amounts of data, but we're carrying very large numbers of packets with small amounts of data. And the packet on Spinnaker has a 32-bit key, which defines the neuron that spiked. It has an 8-bit header, and there's an optional payload that typically is not used. And the way we route these is that those packets are presented to an associative memory, a ternary CAM, where the key is looked up, and if a match is found, then the bit vector is read out of a connected RAM, and that determines the number of destinations that packet should go to. So one incoming packet can become up to 24 outgoing packets with 18 local processors and 6 interchip links as possible destinations. And that allows us to implement routes which look like generic trees across the whole machine. And the example shows here packets going from the node at 1,1, the red node towards the bottom left, aiming for the 3 yellow nodes at the right, and they follow the path as shown on this particular slide. So that, if you like, is the key innovation in Spinnaker. It's the thing that distinguishes it from the communication system in other large-scale machines. It's highly suited to the problem of modeling spiking neural networks. It may not be much use for any other application. So this is not a general purpose compute platform. It's designed specifically to be good at the one thing. In order to make the machine usable, we don't expect our users to be able to write real-time ARM code. So we work from a standard high-level description, which is typically in a language called Pine. Pine simply stands for Python Neural Networks. And this allows you to write a piece of Python which says, I've got a population of this sort of neuron, and I've got another population of that sort, and I have a projection from this to that that has these characteristics. So you can describe quite big networks in relatively modest size source programs. And then we've developed effectively a software flow that takes that Python apart, works out how to map the components onto the machine, and then loads the stuff onto the machine to run it. Pine is quite widely used. You can run Pine on your laptop using a simulator such as Brian, so you can develop a network description, test it out on your laptop, and then run it on Spinnaker if you want it to go faster. So this allows us to build machines. We have the basic chip there with 18 processors in. We can apply that package at high density because the 18 processors between them burn no more than a watt. So cooling the machine is very straightforward. There are no hotspots in it. We put 48 of those packages on a circuit board. It looks a bit like a square, but with the top right-hand corner missing. It is, in fact, topologically a hexagon. So each board has 6 neighbors. And the communication between boards is handled by high-speed serial cables from the FPGAs at the top of the board. We can then assemble those boards into systems of almost arbitrary size. And last month, we achieved our initial objective of having the million-core machine switched on. This was more an excuse for a celebration than a major technical milestone. We had a big party in which we did a live boot of the machine, where, much to my relief, 1,010,000 cores reported for duty. We didn't know what the number was going to come out to be, although we tried it a few times, but I was pleased that it began with a 1. The machine has quite sophisticated fault tolerance techniques built in. There are 1,036,000 cores actually physically in the machine, but some of those are used for fault tolerance to improve the silicon manufacturing yield, and some are basically blacklisted because they've been found to be unreliable. So the way the machine comes up is a little bit variable, but it did the job on the day. It's not the only machine. It's the biggest by a long way, but we've been building Spinnaker systems since 2011, and there are now about 100 Spinnaker boards out with various groups around the world, from Boise, Idaho on the left to Auckland, New Zealand on the right. You see there are several here in North America. There's a rather high density around Europe, which is not surprising because a lot of the work is now supported by the European Union Human Brain Project. So, what can you do with this machine? Well, it was designed for modeling biology, and an example of a small biological system, but one that was very challenging to get operating correctly, is a very detailed model of a single cortical microcolumn. That's about a square millimeter of cortex, and it contains 77,000 neurons, 285 million synapses, and so on. At the time we ran this to publish the paper, details of which are at the bottom of the slide, this particular job took a lot of processors to model. In the 6 months since then, we've used this as a benchmark for tightening up the code a lot. So at the time the paper was written, it took 8 hours to run this model. It now takes 8 minutes. And the runtime is also more efficient. But this model was ran both on Spinnaker and also on a high-performance system at Jülich Supercomputer Center in Germany, and then we can compare the results to check that what we're computing is what we think we're computing, using the supercomputer results as a kind of golden reference to compare the Spinnaker results against. So that's a biological model, and our plan next is to scale this up to a larger area of cortex. We'll be doing that over the next few months, again, in collaboration with Jülich. We've also done some work on less biological models. One example is shown here. This is a network which solves, using stochastic principles, constraint satisfaction problems, of which the most visual example is solving Sudoku. It can solve the hardest class of Sudoku puzzles in about 10 seconds. It can also solve other CSPs, such as map coloring and icing spin systems. At last year's Human Brain Project Summit in Glasgow, we had the chief executive of D-Wave come and give a talk, and of course D-Wave sells a quantum computer which works on the basis of quantum annealing. Not surprisingly, the class of problems you can solve with that kind of quantum system is pretty much the same as the class of problems you can solve with stochastic neural networks, because they're both effectively implementing annealing algorithms. They're different implementations, but they do similar things. And the comparison there, of course, is that the D-Wave solution was much faster than Spinnaker, but then D-Wave is quite a lot more expensive. So there's a price-performance trade-off. Now, we've been developing the current Spinnaker machine for quite a long time, and a lot of work is currently going on into using what we've learned from that machine to develop its successor. And we're using a much more aggressive process technology for this new chip, which is imaginatively called Spinnaker II. And with today's technology, we can fairly easily increase the number of processors from 18 to 160, and increase all the other system components in proportion. So we can effectively achieve something like a 10x improvement in the functional density and the energy efficiency of the system using a more up-to-date technology. And this has been taken as far as prototyping the processing subsystem on silicon. That's come back from the fab and is currently being assembled for test. And the kind of things we've learned from Spinnaker I are reflected in the changes we've made to the basic design of Spinnaker II. So on Spinnaker II, we're implementing very fine-grained power management using dynamic voltage and frequency scaling. And we've shown that we can do this on a very fine granularity, so that each processor on Spinnaker II, which is modeling a population of neurons, typically using 1 or 0.1 millisecond time steps, we can effectively assess the load in each time step and adjust the DVFS setting up or down according to the load. We also note that a lot of the neural models spend their time computing exponentials, which is relatively expensive, particularly on an integer machine. And so Spinnaker II will have accelerators specifically to improve the efficiency of exponentials and similar functions. But most importantly, all of these models make extensive use of random number sources Spiking neural networks are generally modeled as quite noisy systems, and you need a good high-quality noise source. And generating very high-quality random numbers in software is quite expensive. It's very cheap to do in hardware. So every processor on Spinnaker II will have a high-quality random number source as an added component. So if we look at the way we're designing a processing element, and this is getting down into the hardware details, the basic units are shown here, and the key features we're adding are this dynamic power management. So everything can be supplied from one of two power rails and switched between them at a very fine granularity. We can share memory more efficiently than we do on Spinnaker I, because, again, we found that to be something that we want to do a bit more often than we expected. We are adding a conventional machine learning accelerator to this chip as well, so that we can make it dual purpose to support spiking networks and continuous, more industrial standard networks. And the slideshow just interestingly crashed again. Yes, the neuromorphic accelerators we've talked about. They are the exponentials and the random numbers. The on-chip communication uses a relatively conventional NOC fabric, and then for those who are really interested in the silicon details, then down at the bottom, this modern technology requires quite a lot of runtime control to reduce the variability of the silicon. And here, the technology is an automatic adaptive body biasing, which effectively reduces the variance of the distribution that the design of the chip has to tolerate. I mentioned the machine learning accelerator. Because Spinnaker II has 160 processing elements, if you think of the typical machine learning task as being integer matrix multiplies, then you can think of the 160 processors as forming one dimension of a big matrix from one perspective. And so what you integrate on each individual processor is more like a column accelerator. But otherwise it looks fairly conventional. It's an integer multiply accumulate unit. And on this technology, it will deliver something in the region of 5 teraops within a 1 watt power budget. So it's quite a respectable machine learning performance. And the kinds of things you can do in the conventional space, which blend some industrial machine learning networks with some of the techniques we've developed for spiking networks, are to look at new learning algorithms that lead to more efficient networks than are achieved through standard error backpropagation. One example of this from TU Graz is deep rewiring, where effectively the network samples synaptic inputs to find optimal inputs to solve a particular problem, and this can be implemented in a way that works within the constraints of the somewhat limited resources available on the chip. And an example here is a small network, Linnet 300-100, and using the limited memory resources on the Spinnaker chip, this can achieve a reasonable accuracy whilst having connectivity below 1%. So if you think of the matrix describing the connections, fewer than 1 in 100 of the elements of that matrix are not 0. And this makes for a very energy efficient implementation. Something like 2 orders of magnitude more energy efficient than implementing the same network on a standard processor. So these are the areas we're looking into. I'll draw the talk to a conclusion. The Spinnaker project's been going for a long time. We've heard quite a lot about SC being in its 30th year. Well, Spinnaker's not quite as old as that, though sometimes it feels like it. It's been 20 years in conception and more than 10 in construction. It's now quite widely used by people working in the spiking neural network area, and we've recently achieved our original objective of putting together a machine with 1 million processors. And the challenge there, of course, as people in the supercomputer business will know, is not about sticking 1 million processors together and switching them on. It's about building hardware and software systems that can use most of what's there whilst giving the appearance of reliability to users. So a lot of work has gone into understanding how to build a 1 million processor system that appears to be reliable, when of course in practice it's never all working at once. We're an integral part of the EU Human Brain Project. While we've been building this machine over the last 10 years, there's been this huge transformation of industrial AI using second generation, i.e. 1980s, non-spiking neural nets. There's a growing expectation that neuromorphics will have something to offer to bringing industrial neural nets down to a smaller scale, perhaps making them more energy efficient so that at least the inference part of the process can be run on mobile platforms. Everybody's expecting developments in this space in the near future, but as I've already said, there's no compelling evidence that this works at the moment. There are a number of neuromorphic platforms out there. I've mentioned a few. Spinnaker is perhaps the least energy efficient and the most flexible of them all, which to my mind makes it ideally suited as a research platform. If, as is usually the case, you don't know what network you want, then you want a flexible platform to work out what you want. Once you know what you want, you can probably go and build it in a more efficient form. But until you know what you want, I think the flexibility is very valuable, and Spinnaker II will continue that trend and improve all the important engineering parameters by a factor of 10. The graphic on the right of this slide was in the original Human Brain Project proposal, and again it shows an interesting scale of energies. What it's showing is the energy required to transmit one spike through one synapse, so one spike going into a target neuron, which biology achieves using 10 to the minus 14 joules. The very detailed biological models that run on supercomputers typically use about 1 joule per synaptic connection. If you go to simpler models on a supercomputer, you can get down to about 10 to the minus 4 joules. Spinnaker runs at about 10 to the minus 8. Spinnaker II will be about 10 to the minus 9. The analog or advanced process digital hardware neuromorphic platforms get down to about 10 to the minus 10. So there's a whole range of options available for supporting these sorts of models, but the winner, as you would expect, by 4 orders of magnitude, is biology. So at that point, I'll stop. Thank you very much for your attention.
Well, we do have time for a couple of questions, if there are any. There are microphones. I can see them in these aisles and probably on the other side. Okie doke, over there.
Hi, Nicolas Erdodi from Open Parallel in New Zealand. This year we heard about Meltdown and Spectre. Can you comment about the security aspects of Spinnaker in whatever shape that you wish?
Yes, so I mean, the Spinnaker hardware itself offers very little support for security, but it's basically implemented as an accelerator connected to a standard small cluster machine. So the security of the overall setup is really a function of the security of the host server. Spinnaker itself, we have 1,200 circuit boards. We generally run a lot of small jobs, and when the job is running, it owns a physical partition of the machine. So the software tools work out how many boards a particular job will require, allocates those boards, turns off the communications around the edge of that allocated area. So essentially the job is is fully isolated from other conflicting jobs. But apart from that, there are no specific security considerations in the machine.
Amir Chastain, University of Virginia. Thank you very much, Professor Furber, for a very interesting talk. So the question is, you mentioned the lack of commercial success of some of the neuromorphic solutions, and I would claim that the reason for that is actually a technical and scientific in terms of the lack of an understanding of training a full network. We know very well how maybe biologically a single neuron works and how STDP and all these other works, but we don't know how to translate that in the same way that backprop does it for deep networks. And from your perspective that you lead this project, that you want to be successful, if you can point out one or two promising directions that maybe are show promise in training neural networks for complex networks.
I think you point out something that's very important, which is there is no learning rule for spiking networks which is as globally successful as is backprop for continuous networks. And that is a weakness of the spiking network project, if you like. I don't have an instant solution to this. People are exploring different sorts of learning algorithms. Some may be promising, some less so. A lot of focus has gone into STDP because, of course, there's very strong biological data showing that something like that is happening, although I think there's increasing evidence that STDP is an epiphenomenon. It's not actually the underlying process. And there are arguments as to whether the highly recurrent nature of the biological network somehow allows the biological system to implement a form of backpropagation that's different in nature. I mean, backpropagation in continuous nets is basically sending signals the wrong way through the network, which clearly biology can't do, at least not that directly. But there may be other ways of achieving the same outcome, but we don't know what they are yet.
Thank you.
We have time for one more quick question. Yeah.
Thank you. Along on the same area of the lack of commercial success, the IBM Synapse team did a really nice PNAS paper, I think it was in August of 2017, where they actually showed they could match the same accuracy as the best state-of-the-art image recognition algorithms at that time. Was that just a one-trick pony, or is there a direction for the future there?
IBM has probably done more than anybody to use neuromorphics in trying to reproduce commercial applications. And yes, there are some interesting results there, but there's some way to go commercially before they become as accepted as backprop in standard networks. I mean, there are reasons to be hopeful and optimistic about this, but there's clearly still work to be done.
Thank you.
Good. All right. Well, I think we're just about done with our clock there. Yeah. So I thank you, Steve, very much for quite an interesting talk.